In this lecture, we will talk about architectural design. What is architecture? Architecture gives us overall system design. For example, before you actually design the internal subsystems of a given software, before you go on to the detailing, you want to grasp the overall design of the software. So, this is a very important aspect of software design, the architecture. We can talk about subsystems, interconnections among subsystems, and collaborations among subsystems. You must have seen architectural diagrams. Architecture is a very common technique to understand a complex system and then to approach system building from architectural point of view, that is top down. Architecture as a concept is applied in many disciplines. For example, you see building architecture. Before the building is actually built, you have an architecture, and after the building is actually built, then the architecture gets refined over time, and then you get all the diagrams of the actual construction. So, why do we need architecture? We are summarizing this on this slide. Firstly, in order to understand a given system, systems are very complex. They may have thousands of components, classes, very big systems. So, it's very difficult to grasp such a system from bottom up point of view, right from say low level functions or data structures. If you take for example an operating system source code, how will you go about understanding such a source code? Will you start reading directly a specific module and then build your understanding about how the entire system is organized, or will it be easier to understand the system if you had an architectural document with you? How many modules are there in the system, how are they connected, what is the overall perspective on your chosen software? So, an architectural document or an architecture of the system makes it possible to understand a complex system. You can organize your development. So, understanding is very important. If after the software is built, if changes are to be required, and before the software is actually built, you want to organize the development itself according to architectural partitioning. For example, in architecture you have identified a few servers, client side components, middleware. Then you can partition your development accordingly. You can organize your programmers according to architectural partitioning. It becomes easier to handle the system if architecture is available or if architectural approach is taken at the beginning. And then it also promotes reuse by componentization. In an architecture, if you identify a few components which are already built, then you benefit from their reuse. When you are architecting a system, you have to also take into account similar products which have been done earlier in your organization or which are available through third parties, or they could be say class libraries or packages and so on. So when you draw your architectural diagrams, when you do your architectural analysis, at that time you can benefit from what is existing. You have to also do an analysis of reuse. What can be reused? So those components, those reusable components, packages, or whatever entities you are reusing in your architecture depends on what architecture you are handling, what level of architecture you are handling. Highest level of architecture, there could be highest level of architectural components which are reusable. So at that level, one has to identify what you are going to reuse and what you are going to build. So architecture is very important from reuse perspective. And again, when you are architecting a system, you might also take into account future reuse in a given product line. A product improves over time because requirements get refined and refined over versions, and then bugs get found out. Then you might want to re-engineer some part of the system. So a product always improves in terms of functionality, performance, its correctness and so on. So architecture becomes very important. It plays a major role in a product line architecture, product family. So evolution is another important aspect that benefits from architecture. The changes and dependencies. In an architecture, overall architecture, you capture dependencies which are at that level, overall dependencies among the modules which are identified in the architecture, or the components that have been identified, that get identified in the architecture. So architecture also drives the evolution process. Product can evolve. It could be due to versioning, or it could be due to specializations and so on. We are going to subsequently discuss different kinds of architectural patterns and so on. So some of these ideas will come again when we look at some specific examples or patterns of architecture. So what are the basic principles which are applied by architects? So these are some of the very important principles which need to be taken into account when you are architecting a system. Abstraction and encapsulation. You must be able to identify the right abstractions at architectural level and then hide the internal information or the internal details through encapsulation. So this is about separating the what and the how aspect. What does the component do and how it does. So if you identify a specific package, say the GUI package, you should know what it does and then separate how the actual business logic, the actual logic, the GUI components are implemented. So for the GUI package, you will be defining the classes which are available from that package, and then there may be internal classes in order to implement the projected behavior outside the given package. So you have to separate what the module does from how it is done, and then single point of reference as far as possible. So when you have a subsystem, if there is a single point of reference into the subsystem, it becomes easier to manage dependencies. If something changes inside the subsystem, it could be reflected through only the single point of reference. Or if from outside, if there are many references into a subsystem, and if the subsystem undergoes changes, there will be dependencies, many dependencies directly outside through multiple points of contacts. So this is another important aspect of abstraction and encapsulation. Then a general principle of separation of concerns has to be applied when you are architecting a system. You must separate different concerns. For example, different abstractions identify different constructs. Every module or every library or every package does different things. The responsibilities have to be separated out clearly. Separation of interface from implementation, so that the external environment or the calling environment only looks at interface identifies the component through its interface, and implementation is different. Implementation is separated. So if you separate interface from implementation, you get various benefits. For example, implementation can change and still the calling environment sees no change because interface is the same. Then separation of concerns can be applied for, say, policies and the core logic, the core business logic of the component or the system. The policies are different and the core logic is different. So if you list out policies separately, if you identify policies separately, and if you have a separate architecture for policy implementation, for example security policies or your login, password, user accesses, so who can access what, access matrix and so on. So if you have a policy architecture separate from the core business logic or from the core business component architecture, then you are separating the two concerns, and it becomes easier to grasp such a system. So you have to identify different concerns and give different architectures for these and say what are the dependencies amongst them. Then separation of concerns can also be applied to user interfaces and transactional logic. You separate user interfaces from the transactional logic or the control logic. So from the interface the system is used. So the interface architecture is different from the actual transactional logic. So from the interface itself you may not directly operate on the low level data entities, but you may delegate calls onto the transactional logic, and the transactions then implement the operations, the functions which implement these business logic. They take care of the requirements of transactions. They identify the data and then operate on the data. They take care of concurrency and so on. So user interfaces are separate from the transactional logic. Similarly, transactions and data are again separate. They can be separately looked at. The data modeling aspect, entity relationships can be seen separately, and transactional dependencies, or that is the process level architecture, can be given separately. So if you separate the concerns, it becomes easier to grasp such a system, and then according to the separation you can also manage your development. So this is a very important principle, and an experienced architect finds out what are the different concerns from different points of views. For example, abstractions, interfaces, implementation, policies, core logic or transactional logic, user interfaces, data modeling and so on. So these are various concerns. Then another important principle that is to be applied by architects is modularity, structuring and organization. So this is very related to abstractions. When you find out your abstractions, you are modularizing, and then you structure them. You structure these abstractions, you structure your modules. So module is typically very close to an implementation level concept. So module is, you can view a module as for example a file implementing a few functions, and then you have structure amongst the modules, and that's your organization of the modular system. So you can look at modularity / structuring / organization. These are different aspects of structuring. Independent modules which are structured, and that gives you an organization of the modules. So the decomposition has to be modular. So again you are applying separation of concerns, but now we are talking about slightly more physical, about the physical architecture of physical systems in terms of modules. Modules are coupled together. So how far should they be coupled? Should two modules depend on each other too much? And within a module, for example, if you are looking at a class as a module, in the class there are private members and there are public member functions. Public member functions access your implementation, that is your private data. Now it may be possible that you can partition your public member functions into two partitions such that they access totally two different sets of private data structures. In this case the module is not cohesive, it is doing two different things. So you have not really separated the concerns. So a module which is a physical manifestation, which gives you an abstraction, is not really a single abstraction. It may be a composition of two independent abstractions, but may have been put together for the sake of convenience. But now such modules might inject a few problems into the system's architecture, because when one role wants to access only one specific activity or specific interface on that module, it also gets access to something else which is not required by that role, and then you are breaking the encapsulation of the system, because you are exposing more than what is required for a given role. So it is very important to design your modules, keep them cohesive, and the roles which access these modules play a major part in this module design. So for example, in object oriented design you could use multiple inheritance, and then if you have multiple inheritance of interfaces, if you have 2-3 interfaces and one implementation of this class, that implementation shares common state or common data structures in order to implement all the 3 interfaces, and again the module is still cohesive. And then the coupling amongst different modules, that is interdependencies amongst the modules, must be as low as possible. If the modules depend too much on each other, then changing one independently without affecting the other module, without having to change the other module, becomes difficult or impossible if there is too much coupling amongst different modules. So coupling and cohesion are very important aspects in modularity. So several approaches have been proposed to architecting systems, and various books have been written on this. One has been mentioned on this slide, and you could go through the list of various references which I have used during this presentation, and the list has been given at the end of this this lecture. So we will briefly look at some of these approaches to architecture. So Zachman's framework is a very important approach to architecture. How to go about architecting a system, what needs to be architected, how many viewpoints are there for a given system, is there only one architecture or there are many architectures or many viewpoints. For example, when you model your software, you have to do static modeling, dynamic modeling, you draw class diagrams, object diagrams, interaction diagrams, activity diagrams, flow charts, DFDs, entity relationships, state diagrams, deployment diagrams. So all these models give you different views of the same software. So how many such views do you have for an architecture? Is there one unique view for a software, or are there many views, or what are the different aspects which you have to consider when you are architecting a system? So many approaches have been proposed, and this area is still evolving, and there is a lot of academic discussion on what is to be architected, how it is to be architected, what are the basic primitives, what are the basic connectors, what are the architectural description languages, how to model or how to represent your architectural models pictorially. There is a lot of research going on in academic community on architecture. We are going to look at some of the existing approaches to architecture. So one important approach is Zachman's framework. It gives us 30 architectural viewpoints. So from 30 different viewpoints you could get 30 different architectures for the given system. Soon we will look at what are those. Then there is ISO standard called Open Distributed Processing. This gives you an approach to architecting distributed systems. It gives you mainly 5 viewpoint reference model. And then there is domain analysis approach when you mainly look at the domain. For example, there are agent oriented systems where you do an analysis based on agents and what are the entities in the domain and how agents are related to those entities. So, for example, if you are building a library information system, you will firstly look at who are the actual agents, that is human beings who operate or who are involved in such a system, the actual domain. So, without having to say start with the software directly, you first model the domain itself and do an analysis of that and then get the domain architecture, and then you can convert it into a software architecture. So, that is a different approach. And then you have a 4+1 view model, which is what was adopted in the unified process architectural model. And there is a lot of academic software architecture research, so which give us many different approaches, architectural description languages and so on. So, we will have a look at some of these. So, the Zachman's framework, now you can go through the website of Zachman Institute of Framework Advancement, and there is a poster available there on Zachman's framework. So, I will show you the poster quickly, but before that we will just see what was the motivation for this framework. So, Zachman in around say 1987 noted that to keep the business from disintegrating, the concept of information systems architecture is becoming less of an option and more of a necessity. So, in order to keep your information together, in order to keep your business together, you need an architecture, you need to organize everything very well, otherwise it will disintegrate soon. So, if you organize, you benefit from the organization. So, architecture was seen as a necessity, and this was a very important quote by Zachman, and he developed this Zachman framework by observing how architectures in engineering, construction and manufacturing managed changes. So, he mainly defined 30 viewpoints based on roles and product abstractions. So, this is role cross product abstraction matrix, and roles are represented in rows. For example, owner's role needs architectures from owner's point of view, designer's role needs architectures from designer's point of view, then builder's role, the one who actually builds the system, needs to see the system's architecture from builder's point of view. The builder is not interested in the software architecture which is from the owner's point of view. And then product abstractions are in columns. So, mainly say what the product is made up of, the data, how it works, the process, and where are the components located, the geometry and the placements. And then there are 3 additional columns: who, that is the people involved; when, that is the time, about the time; and why, which is motivation. And 2 additional rows which are planners and subcontractors roles. So, if you take a role and a product abstraction, you get a specific architecture, and that architecture is useful for that role and for the given product abstraction or for the given aspect of the product. Say if you are interested in builders what, then you are looking at the actual entity relationships of data. So, what, when you talk about what, you are talking about data. The builder is looking at the data which he actually wants to build. So, you may be looking at the data structures or the entity relationships for designing of tables and so on. How aspect captures the processes or the control part, where aspect captures the locations. So we will just quickly look at this Zachman's framework. So this is a poster from Zachman Institute of Framework Advancement, and you can download this from www.zifa.com. So you can see those different viewpoints, 30 different viewpoints in this poster. Say we will look at builders what aspect. This is the builders what aspect, the green one shown here. So you are looking at physical data model. So you have the entities, the segments or tables and so on, or if you have data structures, your relationships are pointers, in the tables there are keys and so on. So this is the builder's architecture. Now if you look at owner's architecture of what, you will get something different. Say for example, you look at, let's look at planners and where, something interesting. So somebody is planning the software. So owner is the one who owns the business and the planner is the one who plans about it. So the where aspect, you are looking at different business locations, and if you go deeper, the where aspect is going to give you more detailed or more focused places, such as the actual machines, or it could be even the actual components, or even the addresses and so on. So what we can see in this Zachman's framework is that we have all these 30 different viewpoints. We are not going to go into the details of all these viewpoints. You can get more information by reading the related websites and books, but this was an important contribution to architecting software systems. So this gives you a very detailed and organized view about how to go about architecting systems. Then we will look at another related model or approach to architecting systems. This is Open Distributed Processing Reference Model, ODP-RM it is called as. So this is for architecting systems that support distribution, internetworking, interoperability and portability. So typically, say you have a distributed system connected in a LAN or in an enterprise which may be connected through an interoperable middleware, and you have components distributed and then they access services of each other. Some of the components may go down and come up during their life cycle, or some of the components may get deleted, the components may change their implementations. You may share the components in the system. So if you look at an enterprise-wide architecture where there are machines distributed and services may be distributed and applications may be accessing these different services, then what are the approaches to architecting such a system? So this is one approach to architecture. So it provides you with the following 5 viewpoints which are listed on the slide. So enterprise viewpoint talks about the purpose of the software, its scope and different policies that are to be followed. The information viewpoint talks about semantics of information and information processing. The computational viewpoint talks about the functional decomposition. the decomposition of the system. We can say modular decomposition of the system. The engineering viewpoint talks about the infrastructure to support the distribution, and the technology viewpoint talks about the mappings between objects and specific standards and technologies and so on. So, we will look at these viewpoints one after the other. For example, a distributed system architecture may give its enterprise viewpoint, which is directly understandable by managers and end users. So, you are looking at the purpose of your business or your software which you are architecting, its scope and policies. So, it includes different permissions, prohibitions and obligations. For example, you may have these active objects or human beings which are important in this business or for this given software: managers, tailors and customers. The passive objects are accounts. Bank managers must advise customers when interest rate changes. This is an obligation. Cash less than 40,000 can be drawn per day. This is a prohibition, and money can be deposited. This is permission. So, this is a very high level viewpoint, and through this the managers and the end users understand the system. So, this high level viewpoint may be described in a description language, and that gives you a view, an architecture of the system. Or you may draw also pictorial representations of the same. Then information viewpoint gives you definitions of information schemas as objects. For example, state and structure of objects. Say in the account object, you may have its state as balance and amount withdrawn today, on that day, on any day. So, amount withdrawn today gives you the total amount that was withdrawn on the day of reference. Then there could be three kinds of schemas for this information viewpoint. The static schema, for example, at midnight amount withdrawn today is 2000. Invariant schema gives you an invariant for your given object. At any time amount withdrawn today should be less than or equal to 40,000. And the dynamic schema gives you the dynamics which are always constrained by the invariant. For example, if you deposit x, then the balance increases by x. If you withdraw x, the balance decreases by x. So, this is very similar to design by contracts, where preconditions, postconditions and invariants can be used. So, this is information viewpoint. When you are looking at informational objects or schemas, you are going to do analysis from these 3 points of view: the invariants, the dynamics and the static attributes or the statics of your chosen objects. And then the schemas may relate objects. For example, in customer object, a customer object owns an account static schema. The dynamic schema, these might be governed by the policies of the bank, and the customer object owns the account static schema, the balance variable, the actual state of the object. This from informational viewpoint. Then from computational viewpoint, you are talking about software components and how are you going to implement them. So, for example, large grain object encapsulations may be thought of as server processes, or you could have subsystem interfaces for packages. Then you can talk about how objects are implemented, how objects offer different multiple interfaces, how they are implemented to project various behaviors or various interfaces for different roles. how they interact with each other. So you are talking about implementations, how the calls are sent, how messages are sent from object to object or module to module. Are they through message invocations, or are they through exceptions, or are there streams, continuous streams? So there are different kinds of connectors. So you are talking about different components, how they are organized, how they are implemented, what are the relations among interfaces and their implementations, and how they are connected through different connectors. So we are listing some more details about computational viewpoints here: interface and inheritance of interfaces, then various aspects about objects, such as how are they created, how do you treat for an interface, how do you search, how do you locate the object, how are interfaces created, how does the actual binding occurs, how are operations invoked. So we are talking about a distributed system, and then in the distributed system you have to actually detail out how the invocation goes from one machine to another. And on application objects there could be different interfaces. Say for example, bank teller's interface and bank manager's interface are different. So you could allow deposit and withdraw on the teller, whereas you can create an account through bank manager's interface. And there could be infrastructural objects involved from computation viewpoint, from the actual implementation viewpoint, that is, you are using some of the existing infrastructure services such as naming service, event service, and so on. Then the engineering viewpoint brings out the distributed nature of the system. So when you are looking at computational viewpoint, you are mainly looking at the objects and how are they implemented, how are they connected, and what are the different computational connectors or relationships amongst them. And when you are looking at engineering viewpoint, you are actually looking at the physical manifestations in a distributed system. How will they be connected physically? What are the different objects from engineering viewpoint? The objects and the channels, the actual connections. For example, your objects may be basic engineering objects which are corresponding to the computational objects which are identified in the computational viewpoint, or infrastructural objects such as, say, protocol objects, your stubs, the proxies and skeletons, and the protocol objects, proxies and skeletons, or binders, or communication interface between the protocol objects, the low level objects which are required to make it possible for a message to go from one system to another. So this is the engineering viewpoint. The objects in engineering viewpoint come out when you are talking about the engineering viewpoint architecture of the system, and not in the computational viewpoint. The computational viewpoint mainly talks about the functional requirements, what are the entities, what are the objects in the domain, and the related processes and the relationships amongst those objects from computational viewpoint. But from engineering viewpoint, you are actually making the system distributed, and you are talking about how this distributed system is going to function together. What are the actual objects, how are they located, where are they located. Say for example, the structure, the engineering structure of the system could be identifying the clusters, the nucleus objects, the capsule of clusters, or a machine node. A cluster may contain many engineering objects, and object can contain many activities, and then you have inter-cluster communication via different channels. So you are talking about the physical aspects or the engineering aspects of the system. You may have a server process in which many objects are held, but this does not come out in the computational viewpoint. There you are mainly talking about core computational objects and relations amongst them, whereas in engineering viewpoint you are talking about the engineering of the system, when you are actually going to build a system. So some more objects come out in this viewpoint. So you have the you carry on or carry over the objects from the computational viewpoint and also add the engineering objects such as say proxies and skeletons, which you don't have to detail when you are talking of the computational viewpoint. If you get the entire architecture in one shot, then it will be too complex to comprehend. So if you separate these viewpoints, you are looking at different kinds of architectures for different roles. So this is another approach to architecting, and this is specifically for distributed systems. And in this approach, you have to also look into various transparencies guaranteed by your system. For example, do you guarantee access transparency? Access transparency hides difference in data representation and invocation mechanism. For example, you may use your server through function calls, but your server may be object oriented, which requires member function calls, or you may have an implementation which is in COBOL, but you have your client which is in an object oriented programming languages, which understands classes and objects and invocations and objects. So this access transparency hides the actual data representation from the invocation mechanism. The invocation mechanism is different from the actual data representation. Then you may have failure transparency. If a component fails, the caller is not aware of this failure, the component may come up. So if a failure is hidden, and you get this failure transparency. Location transparency talk about hiding the location, the information of the location while finding and binding to an object. So internally, if you use a naming service and then the internal mechanism, the proxy may find out where the object is and connect to the object, and the actual caller is not aware of the location. Then you may have relocation transparency, which masks the changes in location of an object from its clients. So the location might be changed. So if this relocation is also hidden, then you get relocation transparency. And then there are other transparencies such as migration transparency, replication transparency, persistence transparency, and transactional transparency. So these have to be looked at when you are architecting the system. What transparencies are you guaranteeing, and how are they reflected through your architecture? What are the different components that are responsible to provide these transparencies? So this ODP approach details all the mechanisms or all the ingredients that go into a distributed systems architecture, which you have to use when you architect a distributed software system. Then there is another approach called 4+1 view model of Kashchen. This gives you 5 concurrent views. Logical view talks about the object model using object oriented design methods. Process view talks about concurrency. What are the different concurrent activities and what are the synchronization aspects? Physical view talks about mapping of components to hardware and then the distribution aspects. And development view talks about organizing the actual software modules. This is very important for your deployment. Say you are organizing it in libraries or different packages. Say you have in Java you have packages, in C++ you have libraries. How are you organizing them in subsystems? And there is also this 4+1, that is 5th view, called use case view, which is very high level users view. Use case is as a very important aspect of software development has been mainly proposed and discussed by Ivar Jacobson, and this is also available in the unified process. So the unified process model approach of architecture is very close to this 4+1 view model, but here the focus is on iterative refinement of architecture. And architecture description is an extract of the models of the system. So say if you use UML for modeling your system, you may have many models such as use case model and your analysis models, design models. deployment model, implementation model. So when you are modeling your system, you extract important aspects from these models and you have an architecture. So that is one viewpoint on architecture. So this contains only architecturally significant use cases. When you are talking about architecture of the system, you are only extracting architecturally significant central use cases, whereas final use case model may contain all the use cases. Similarly, architecturally important design aspects from design model you can extract, and final version of the architecture is extract at the end of elaboration phase of your software life cycle. So this is a unified process approach to architecture, and architecture gets developed iteratively during the elaboration phase. So the focus for the architectural team is on significant structural elements. You are talking about subsystems, important classes, components and nodes. So here, as you refine your architecture, you might refine your use cases and accordingly might refine your architecture. So this is another important aspect of architecting systems, or this is one approach to architecture. Now we are going to look at some of the commonly occurring architectural patterns, so which you see in different architectural in all of these architectural approaches. So we are talking about structuring your components in the architecture. For example, you are looking you may have layered architecture. You may have peers, client servers, pipelines, filters, blackboards, facades, brokers, model view controllers, microkernel, reflection and so on. So these are some of the important architectural patterns. So just as we have design patterns for designs at class level, how classes are put together through inheritance, aggregation, using and so on, different relationships. Similarly, here this is mainly about high level organization of your modules, subsystems, the structure amongst high level packages or high level entities. So these are some of the commonly found patterns in architectural documents on in architectural examples. So for example, you have seen these layered systems often. So you can build a layered architecture of a given system. So you can see here an example of an operating system architecture. In the top level you have applications which access system calls. In the second layer, in the third layer you have the kernel upper half, in the fourth layer you have the kernel lower half, and the base layer you have the hardware. So this is a layered architecture, and the top layer has a higher abstraction than the lower layer. The top layer accesses the lower layer, and the lower and in any given layer given say you talk about system calls, it accesses or it uses kernel upper half, and it gives an interface to applications. So this is the way to structure layered architecture. So you can decompose your system in terms of layers. Another way to decompose your system is in terms of peers. For example, you have a LAN on which there are many machines, and from any machine you can access any other machine. You can deposit files from say machine 1 to machine 4, or machine 4 to 1, or 2 to 3, 3 to 2, 3 to 4 and so on. So you have peers which are sharing data amongst themselves. So this is a peer architecture. This is not a layered architecture because you don't have layers sitting on top of each other. You may have client server architecture, where the client component accesses services projected by the server, services offered by the server. So you have a diskless machine which uses a remote file server, or a student's machine which uses a central file server. So you talk about client servers. Web services, for example, web services are your web servers. So the same idea is applicable to different contexts. You may have a client server model on a LAN, or even on internet, or that is your web service model, or at the low end even you may have it even in a sequential program where you are talking about a client object and a server object within a program. But you are, when you talk of client server, mainly your focus is on distribution aspect and the decoupling in through different processes. Then you have pipelines where you have stages one after the other. Say in a compiler you have lexical analyzer, then you have syntactic analyzer, you have code generator, code optimizer, and so on. So these are different phases. So you have a pipeline architecture. You could have transactional flows in an academic system, say online academic network in a university. Say first the student pays the fees, or you take a note of this fact that student has paid the fees through the bank, obtain, and then one can obtain the identity card. After that you have two transactions, one can subscribe to the mess or go on to course registration simultaneously. So you have these transactional flows and dependencies. Then you may have filters in your system. So you have an email receiver, then there is a virus filter which filters viruses from the attachments, and then you have a spam filter which filters unwanted emails or spams, and then you have a local dispatcher which dispatches the emails received at the local dispatcher end to local machines and users. So you have filters in your pipeline. So some of the components in your pipeline are filters, not transformers. Then this is an example of a blackboard architecture. Say in a parallel computing scenario where you are having shared memory, you may have a shared task space in which the task generators deposit tasks and from which the task executors pick up the tasks and execute them, and then they deposit the results onto the shared result space. So we have these shared task space and shared result space as two different blackboards which are used by generators and executors simultaneously. So this is a shared memory or shared space architecture. Then this is another architectural pattern called facade. So you have a subsystem in which there are many classes. This could be a package, and the package is the interface of the package is given through one class called front end, and the internal classes are hidden. So this design pattern is also important from class level architectural point of view. So facade is an important architectural pattern or the way to organize your component architecture. Then broker is another pattern which is seen in distributed decoupled component systems. The broker is responsible for coordinating communication amongst different components. It can forward requests from one component to another, or it can get back the results and send and the results are dispatched back to the calling component. Along with the results there could be exceptions or only exceptions and errors which also need to be passed back to the callers. So this broker architecture allows dynamic addition, deletion and relocation of objects. How that we will see from this slide. So for example, you have this broker sitting in the middle, and you have a client and the server component. The client accesses the broker through proxy, and the broker sends the calls to the server through the skeleton. So if you change the server, the client still is not aware of this because it goes through the broker. There is no direct connection to the server. So the results from the server go back to the client through the broker. So this broker architecture you can see in distributed systems such as Corba. Then you have MVC architecture, which is model view controller. You have a model which you can see on the left bottom corner. So these are your different entities or your data, and you have a view of this, and you have a controller which makes changes to the model. So the changes to the model must be reflected through different views. Now you can apply different collaboration patterns for amongst this view, between this view and the model. For example, the view might periodically check if the model has changed, or on every change the view may be notified. So there could be push pull models applied for interactions or for consistency among model and the view. So this is MVC architecture. Then you have microkernel, where you develop higher functions on top of, you first develop very low level routines. Say for example, you have microkernel operating systems where you have core assembly routines on top of which you can first develop core functionalities, and then you can have additional functions. The calling application might use core functions and additional functions both, but you have a small kernel on top of which you can develop higher level or more detailed facilities, or you can extend your functionalities through additional functions. So this is microkernel type architecture. And then another important approach to architecture is frameworks. So frameworks are almost partially completed applications. So framework architectures is a very important concept in large scale software development or large scale software reuse. So a framework is instantiated as a product. So for a product family, the framework is very important. Say you may have, if you are specializing in library information systems or academic systems or banking system, you may already have some concrete classes, partially implemented classes for that domain. For a given application, for a given customer, you may specialize this framework into a specific product. So you have frozen spots and hot spots which are projected in this diagram. So on the top level you can see concrete classes in this framework, and then hotspots are abstract classes or abstractions. So concrete classes in the framework make calls to hotspots, and the hotspots are not implemented in the framework, they are to be specialized. So the specializations can be seen at the bottom. So the specializations plug implementations to hotspots, and the concrete classes uses the hotspots. So the framework implements concrete classes, and the hotspots are to be implemented when you actually specialize this framework to get a product. So the specializations implement hotspots, and concrete classes use these hotspots or abstractions, abstract classes. So say for example, if you take a graphical editor in which you may have shape as an abstract class, and the actual shapes may be specialized, and the framework, the editing facilities such as copying of shapes or moving up shapes, rotating of these shapes can be implemented already in concrete classes. So a specific framework for say drawing UML diagrams or drawing DFDs or drawing flowcharts can be specialized in this product family through these specializations, whereas the application is already partially implemented through concrete classes and hotspots. So this is an important architectural concept, frameworks, which gives you large scale reuse or large scale benefits from reuse in product line architectures. Now in the last slide we have this list of references, and there are many more related research papers and books, and you go through some of these and get more detailed perspectives on architecture, and you could put in practice. So architecture is very important from overall point of view, so that the system becomes understandable, and then you can base your development on your architectural decomposition.